NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
I brought out some admirers, apparently. Hello, and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, and our monthly public lecture, which we call the Von Karman series. I'm Preston Dykes from the communications office here. Well, they're small, they're modular, they're relatively inexpensive to build and launch. Our topic this month is CubeSats and SmallSats. It's a field with immense potential, and it's led to an explosion of new ideas in the last few years. Our two speakers today are helping to lead that innovation here at JPL. Now, both Travis and Annie began their journey as engineers working on small satellites. And as you'll learn, it's a field that offers a lot of opportunities for students and others who are early in their careers to play meaningful roles in actual spacecraft missions, which is pretty exciting. So after our two talks, we'll take questions from here in the audience, and if you're watching our live webcast, we'll work in a few of your questions. You can submit questions via the chat on YouTube. So to start us off, our first speaker is a systems engineer here at JPL, and he's worked on a variety of small satellite missions with interesting names like RainCube and Lunar Flashlight. He serves as a subject matter expert for small satellite missions, concepts that our teams here that are formulating and designing new missions. He's a graduate of the University of Texas at Austin, and he's been with JPL since 2014. Please welcome Travis Imken.
All right, well, thank you for the introduction, Preston. This is really exciting to be here. When Anne and I were talking yesterday preparing for this talk, we both realized that we've worked on a lot of small satellites over our years. And although we've had the awesome opportunity to work on them here at JPL, we've also been able to work on them in school as part of our path to get here. So a little about myself. As Preston mentioned, I'm originally from Texas. I ended up getting both my bachelor's and master's from the University of Texas at Austin in aerospace engineering. Here's a picture of me before I had a beard. This eventually led me to here at JPL to be a systems engineer since 2014. And in my time, both in university and here at JPL, I've had the opportunity to work on 7 different CubeSats. This beautiful one you see here is RainCube, a mission I worked on from formulation through flight right now, and as well as 2 other missions that have also been launched. This is Bevo 1 and Bevo 2. For those of you not up on your University of Texas trivia, that's the name of our cow mascot, Bevo, so we named it as such. I've worked on 3 others that are still in progress, and there is one more, but in this case, I'll just say a picture's worth 1,000 words on when that one tried to get into orbit. So what is a CubeSat? Well, the CubeSat standard was first imagined 20 years ago, in 1999, by Jordi Puig-Suari and Bob Twiggs. And the CubeSat is this. This is what we call a 1 unit, or a 1U for short CubeSat. It's 10 centimeters on each side. If the walls were solid and you were going to fill it with water, it would hold exactly 1 liter worth of liquid. And once we finish cramming all of the metal, electronics, boards, and other wires into this volume, it ends up weighing about 1 1/3 kilograms per unit. So a CubeSat is miniature. You can hold it in a hand. You saw me holding it on the previous slide. Here's a blown up picture of our IPEX CubeSat. The CubeSat is also designed to a common standard. So in this photo, we see 3 1-unit CubeSats, and although they all generally conform to the same outside form factors designed to fit within the dispenser, you can see they look radically different. They have different solar panel arrangements, and if you look closely at that one on the right, you can actually see those yellow stripes. Well, that team actually decided to use yellow painted spring steel tape measures, just like you get at Home Depot, and they're using those as their antennas so they can communicate back to Earth. So instead of building 3 CubeSats, some clever people have said, well, hey, why don't we just stack them on top of each other, fill in the space in between, and make one monolithic satellite? So this is what we have here. This is what we call a 3-unit CubeSat, or a 3U for short. Basically, we've taken all that volume and then stacked it up. From there, the standard gets bigger. We could double this in width, would make it what we call a 6U, like the RainCube satellite I showed in the previous slide, and they can get even bigger. 12U, 18U, 27U, it's all modular. Another unique thing about a CubeSat is they're all delivered to space inside of a dispenser. So this is a 6U dispenser. It's for the Marco CubeSats that Anne will talk about later. So there's a CubeSat inside of this box, and you can actually see there's a door here on this edge that would actually open up and fling the CubeSat into space. This is something that's unique about the CubeSat platform. They're all delivered usually into space inside of a box, and I'll talk a little bit more about why that is on a later slide. So our talk tonight is about CubeSats and SmallSats, and I'm mostly going to talk about CubeSats, and then Anne will talk a little bit more about some of our SmallSat concepts in her presentation. But it's important to remember that a CubeSat is part of the SmallSat family. Now, one thing about SmallSats is they're not exactly new. In fact, the very first spacecraft that the United States ever launched into space was a SmallSat. So this is Explorer 1, I think from 51 years ago. In this picture, I feature kind of some what we would call SmallSats. So in this case, you can see some fundamental differences from what I talked about in the CubeSat. You can see they're bigger, maybe the size of a mini fridge. You can see they've kind of taken different shapes and sizes depending on what needed to be done for their missions, what their payloads were. And you can also see that they're the primary payload on top of this rocket. However, bringing back our old friend RainCube, being constrained in a box doesn't actually affect the shape that your satellite takes in the end. In our case, though, we went up in a nice square form factor. We opened up our solar panels, you can see here at the bottom, and we ended up unfurling this giant half-meter mesh antenna so we could complete our science mission. So something that's really exciting about CubeSats is how similar they are to spacecraft, but how different they are to some of the traditional spacecraft that you've known of from JPL, for example. What's key is access to space. So this is a picture from the Indian Space Agency. This is a launch from 2017. And I want the audience to guess here, how many CubeSats do you think were launched on this rocket? Anybody? One. Okay, I heard one. It's more than one. Otherwise, I wouldn't be showing this picture. Any other guesses? 100. Okay, if you said 100, you're really close. There were actually 104 total satellites launched on this vehicle, 103 of which were CubeSats. So that's a really big deal. I also like to say that CubeSats are different than big spacecraft because they have what's kind of a constrained complexity. On our big missions, like the ones you see in this room, you can see they take the shape needed to complete their science mission. In our case, looking on the insides of RainCube, you can see when we had to fit within the box form factor, we did our best to make this engineered web of cables, RF connectors, and electronics boards. You can't imagine how we could actually stuff any more in here. So that limited the amount of redundancy we can have, and for other missions, it might limit the complexity of your payloads or even the number of payloads you carry overall. CubeSats also leverage commercial components. So if you learn one acronym tonight, the acronym you should learn is COTS. That stands for Commercial Off the Shelf. A COTS component is something like the electronics you have in your laptop, in your smartphone, or maybe even your Fitbit. So generally, these are components that are very powerful in terms of like performance, but also use low power in terms of watts. There's also a lot of availability. So you can go online, you can buy components very cheap, you can iterate, and you can pack a lot of performance into these small packages. Finally, something that makes CubeSats unique is how many that you can simply launch at a time. A lot of the missions we have at JPL, you launch one, maybe two spacecraft that are similar to each other. This is a picture I borrowed from Planet Labs, and each of these spacecrafts is called a dove, and they actually launch a flock of their doves into space. So all of these CubeSats are essentially copies of one another. They all have an imaging payload. And when they're launched together, they actually spread out within the orbit and take images one after another in space of the same ground target. And that gives us unprecedented access at seeing kind of the small time variation that you wouldn't be able to get if you only had one big spacecraft, maybe flying over the same point every hours, days, or maybe even weeks. So I want to come back and talk about access to space, because I think this is something that makes the CubeSat platform truly unique. So this is a picture of a satellite called NPP. You can see a white frocked person in the lower left corner for scale. And I need audience participation again. Can anybody find the CubeSats in this picture? Okay, well, I drew a nice yellow circle. So they're actually just stuffed down here in the corner for scale. So this is three unit CubeSat dispensers. And this has been the more traditional way of how CubeSats get into orbit. So there's a very big payload that you can see here. They've paid most of the cost for the rocket. They're paying to get into the orbit they want to go to. And the CubeSats say, hey, you've got extra volume, extra mass, let's tag along. And they pay a much reduced price to get into space. The only consequence of that is you ultimately kind of end up in a similar orbit similar to where the actual paying customer is going. Another method we have is through the International Space Station. And this is a rather Rube Goldberg process. So the CubeSats are actually packaged up as cargo with the astronauts' food and their water. We're inside the pressurized and environmentally controlled volume of the cargo capsules. And When they go up to the space station, the astronauts will then actually pull the CubeSats out, carry them through the station, or float through the station, I suppose. And then when time is right, they'll actually open up the airlock on the Japanese module and slide these dispensers out, and then they fire the button and the CubeSats come sailing out. So here they were with the solar panels of the ISS behind us, and you'll see the RainCube, which is on the left, and then HaloSat on the right, sail off to begin their science missions. I think the ISS is actually the most exciting way to launch CubeSats because you get astronauts taking pictures of your satellites coming out. Something else that's being developed is really unique. So in this first picture, I showed you the CubeSats are up at the bottom. In this case, though, the CubeSats are up at the top. So this is a picture of the Electron rocket from a company called Rocket Lab. And they're part of an initiative to develop small launch vehicles that are dedicated to launching CubeSats. So before that fairing installed, this is actually what it looked like at the top of the rocket. So if I counted right, I see 15 different CubeSat dispensers. And this is part of NASA's Alana 19 mission, which actually launched 10 different NASA CubeSats amongst other missions from these. So in this case, similar to the first picture I showed, these CubeSats mostly all got to kind of pick the orbit that they went to. It was one that was desirable to them, although they all ended up kind of going to the same place. So time for some data. And I have one big chart. So starting in 1999, people were developing CubeSats. The first launch we have recorded is from 2000. But you can see through 2012, we really ended up launching no more than about 25 a year. In 2013, you can clearly see that exploded. So my colleague Mike Swartout at St. Louis University collects this data. And he's done a lot of work into defining who's building CubeSats and what's going on. So the first category here is hobbyists. He defines this as organizations such as universities or amateur groups that are doing this for the learning experience or perhaps for other kinds of development activities. And when I was reading up on this, I actually learned that even though I thought I was really cool doing CubeSats as a university student, today there have actually been high schools, middle schools, and elementary schools that have actually launched CubeSats into space. So the next category we have is traditional. Traditional would be institutions much like JPL, where we're used to building big spacecraft, and we build small spacecraft, perhaps tailoring some of our practices down to meet the CubeSat form factor. The next category is yellow. It's a made-up word. We call it the SmallSatters. So this is a group of companies whose core business model is based around the SmallSat platform. JPL loves to partner with these companies. In fact, RainCube, we built the radar payload for RainCube, and a SmallSatter company called Tyvak down in Irvine built the spacecraft bus that hosted our payload, and then together we flew that mission together as RainCube. Now you're saying, okay, well, what's green? That makes up most of this plot. Well, green is actually a subset of the SmallSatters, and these are the SmallSatter companies that are actually in the business of making constellations, much like the figure I showed of the planet flock of doves. In this case, you can see that once the constellation company starts launching, they launch a lot. And you really see this big bump here in 2017. So that launch of 103 CubeSats that was on the IceRA launch, 88 of those were from Planet. So if you were to add all of this up, I think this is the big take-home message of the night, is that through the end of 2018, we have launched over 1,000 CubeSats into space. A few more statistics. This has actually been done by over 256 unique organizations across 54 countries in the world. So this is truly a worldwide initiative to get access to space. Another question that will probably come up in the Q&A, so I'll address it now, is, well, okay, you've launched 1,000 into space. What about the space debris problem? And that's something that's kind of unique to the SmallSat form factor, since most of them stay in low Earth orbit. They're actually only a few hundred kilometers above Earth. And there's actually sufficient atmospheric drag that most of these actually will end up deorbiting within a few months to a few years after their launch. That's why in the constellation sense, they actually have to keep launching more CubeSats because they have to replenish the ones that are falling down. So I borrowed this chart from the headquarters, the Small Satellite Coordination Committee, courtesy of Charles Norton. And this is the subset of NASA CubeSats and SmallSats, and we call this the fleet. These are both operating missions and future. Now there's so many to count here, but I guess you're all here for a few hours tonight, so we can probably go through each of these one by one if you'd like. Well, I tease. I'm only going to feature 4, and then Anne will feature many more that are on this plot. So IceRA in white is a technology and exploration mission. We have Asterius, which is an astrophysics mission, and then Tempest D and my own beloved RainCube, which are Earth science missions. All right, so IceRA. IceRA is the Integrated Solar Array and Reflect Array Antenna Mission. This is a picture of it here. So now that you're all experts, can anybody guess the form factor of this CubeSat? 3U. All right, good. You're up to speed on the lingo. So you can see IceRA also didn't want to stay in the shape that they went up in. So this is IceRA's reflect array. You can kind of see the circle pattern here. And this mission was demonstrating high data rate communications. So there's a radio frequency feed right here that then bounced off of this antenna and then beamed high data rate Ka band communications back to Earth. So here's a picture of it in orbit. So you can basically see the same view, although you can get a little bit better view of the reflect array, the feed view up here. Now, of course, the acronym said it was integrated solar array and reflect array antenna. So a technology infusion we had on IceRA was we actually took the reflect array, and on the opposite side, and I did my best to find a picture, but I couldn't, but on the opposite side, there's actually a solar panel. So all of the solar arrays were able to flop out. You're able to generate lots of power when you pointed that antenna at the sun, and you could also then turn and then point that antenna down at Earth when you needed to do the high data rate communication. Something else that was unique about IceRA is that their primary mission was to demonstrate this high data rate communication, but they had extra payload volume. So the Aerospace Corporation included these 3 infrared cameras that you can see right here. And here's a picture from one of those cameras. This is from the shortwave infrared camera. This is actually a picture of Lake Superior. And the frequency of this camera was tuned to actually differentiate between land and water. So the white you see here is all of the land surrounding Lake Superior. So this is a really cool kind of technology innovation demonstrating these new infrared cameras and then as well as this high data rate communication and synergistic combination of the solar panel with the antenna. All right, so Tempest D, and then I need to check my acronym here. This is the Temporal Experiment for Storms and Tropical Systems. I don't know how they got Tempest out of that, but the D stands for the demonstrator. So Tempest D is this bird-shaped mission you see here. Again, does anybody want to guess the form factor? 6U, all right, yes. And it carried a radiometer, and the radiometer actually viewed out of this hole right here, and it was 5 different channels. So the first channel is 87 gigahertz, and in this case, the 87 gigahertz is really just sensitive to saying where is water. So in this animation you see here, you can basically see the vapor, clouds, and precipitation. As expected, you have a lot of weather here around the equator, kind of between the tropics, and of course the land masses you see around are red because there's not a lot of precipitation there. Although if you look really closely on this animation, you can actually see that it can pick up some of the big lakes in Africa. The other 4 channels of Tempest D radiometer allow it to actually get cross-sections of the atmosphere, each a few kilometers apart. So the 181 gigahertz you see here in the top right is actually the highest cross-section. Then we step down to 164 gigahertz in the lowest cross-section. So in this image, we actually, in September of 2018, Tempest D flew over Typhoon Trami, which was just off the coast of Japan, and was able to get these 4 horizontal slices of the storm. So the other Earth science mission to feature is RainCube, which, like I told you, is my own beloved mission. So here's a big version of it. So we had this giant deployable antenna, and of course, seeing that we had something big and complicated deploying, we had to put a camera on board to catch it. So you can actually see here our motor driving our antenna out of the inside of the CubeSat. It actually filled up this volume kind of inside. And then as we were going over Earth, it took about 3 minutes to actually pop it out. Now, fortunately, both RainCube and Tempest D both flew over Typhoon Trami around the same time. So here you can see RainCube took a very similar track over the storm, right over the eye, which happened to be very fortuitous, and we ended up producing this plot. So if you look closely, here's the left wall of the hurricane, and we actually got the left wall of storms right here. The eye is this space right here in the middle, and then the right wall right here. We then continued along our way until we actually caught another storm later in our track. So you might see where this is going. We had two CubeSats. They both viewed the same storm about 5 minutes apart. What can you do with that? So refresher, here's what the data looked like. And we did some data processing, and we actually ended up with this graphic. So this is animated, so don't let it get too dizzy because it will spin around ad nauseum. So this is taking those horizontal 2D slices from Tempest D. You can count the 4 slices here. Then with the vertical slice of RainCube going up and down. And we're actually able to get a really interesting cross-section of what Typhoon Trami looked like. Now, although this was kind of an opportunistic measurement, I think this is really exciting for what you might have in the future. Imagine that you might have constellations, just like the imagers we have from Planet Labs, but constellations of these radars and radiometers where they could be flying one after another, each collecting the same measurement, or perhaps spread out in space, so you're getting different vertical profiles side by side. Then you can combine all of these measurements together, and you actually get a really unique insight into the evolution of storms. Because when you have rapid passes of the same storm system, you can begin to understand the short timescale evolutions of these storms, which can be a huge boon to weather and climate modeling. So my last mission I wanted to talk about is Asteria, and that's the arc-second telescope for enabling research in astrophysics. So Asteria was a 6-unit CubeSat. They also have these flop-out solar arrays here. Now this blue thing you see here is actually their main payload. That's their telescope. So Asterius' mission is to hunt for exoplanets. And if you came to last month's Von Karman talk, you learned all about how to find exoplanets. So although the Cube satellite platform does its best to get very still in space, and comparatively it gets pretty still, if you're staring at a star very, 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 very far away, you need to be very precise in how you look at it. So this telescope was actually able to take out all of that noise that was still in the CubeSat platform and focus in on one target. It also achieved an incredible thermal stability, which was needed to dwell on those targets for some time. So what it looked like, and the animation didn't work on this one, but this is essentially what Asterius cameras, the raw data, look like. So this orange dot you see here is essentially the star, and it would actually just stare at it. And if this animation played, you would actually see that the orange dot would not move throughout all of the frames. So it was incredibly successful. And what Asterius' mission was doing is it was waiting and staring and waiting for a planet to actually transit in front of that star. So as it stares at the star, it would actually be looking for a dip in the brightness with this signature U shape here, and that would actually signal that an exoplanet had passed in front of that star. So this is a really exciting mission. It's something that has really never been attempted on the CubeSat platform to date. So here we are back at this chart, and I'm wrapping up on my few missions. But the future is really exciting, or we've had some exciting missions that have led us to this point, and we have a lot of exciting missions coming up. You can see that I've just covered a few of these. We have many more Earth science missions, technology missions, and astrophysics missions, but we also have missions that are getting ready to explore throughout the solar system, and Anne will tell you a lot about that. So with that, I'd like to say thank you.
Great, thanks a lot, Travis. Appreciate that. Well, I assume you all feel like you're CubeSat experts now. I think you should, because I heard 6U, 3U. You guys are shouting out the form factors like experts. Well, I'm sure at this point you're ready to learn a little more about the potential of these fascinating little spacecraft. So our next speaker will delve into some of the really neat things that we hope to do with these spacecraft going forward. She's the lead engineer for JPL's collaborative design team for CubeSat and SmallSat missions called Team XC, and the C is for CubeSats. She served as a systems engineer on the first CubeSat mission sent to deep space, the Mars Cube 1, or MARCO mission, which last year successfully demonstrated that CubeSats can operate at destinations far beyond Earth. She's an MIT graduate who's been with JPL since 2016. Please welcome Dr. Anne Maren.
Thank you, Preston. Hello, I'm Anne. I'm going to be talking about what happens, or what we view for CubeSats going beyond low Earth orbit. So just like Travis, I started in CubeSats in the university program. So I actually wanted to be an astronaut when I was about 9 years old. I dug up this photo of me at a Girl Scout space camp. The fun fact, about 2 years after this picture was taken was when CubeSat form factor was actually invented. So I had no idea about it at the time, but that's a pretty cool overlay in time. I did my bachelor's in aerospace engineering at the University of Michigan. That's when I was there, they were just starting up a lab that worked specifically on CubeSats. I worked on a couple things, particularly with my senior design class, actually designing a CubeSat that later flew after I graduated. And then at MIT, I helped design and build and fly the very first CubeSat that MIT built. So just like Travis, I've worked on, I think, counting and with differing levels of involvement in the missions. I worked on about 7 CubeSats, including the ones at JPL. So I've been at JPL for about almost 3 years now, and here I've worked on the MARCO mission, going to deep space, and another mission going to deep space called NEA Scout that I will also be talking about later. But with these CubeSats, because they're all about the same size, there's very little difference between the integration and the experience you get in a university setting versus then what you do turning around and working at a place like JPL. It's an amazing opportunity, and it's surprisingly applicable for future careers in space exploration. So what do I mean by beyond Earth? And when you fly a CubeSat into, or any satellite, into lower Earth orbit, there are certain advantages, there are certain things you can take advantage of. So of the 1,000 CubeSats that Travis mentioned launched, only 2 of them have actually gone beyond low Earth orbit. So some advantages of being in low Earth orbit, you're only about a few hundred kilometers away from the surface of the Earth. When you're trying to communicate to a satellite, you have a fairly wide range of bandwidth that you can play with, and so you can have ground stations all over the world at different frequencies. There are universities that even build their own ground stations to talk to these satellites. You can also take advantage of systems in orbit around Earth, like global positioning systems, or communications networks like Iridium and Globalstar, to actually figure out where your satellite is and have another way of getting the data down. And another cool thing that you can do around Earth is actually take advantage of its magnetic field. So if you're flying close enough to the surface of the Earth, it kind of acts as a shield for high energetic particles that come from the sun and for interstellar space. You can also use the magnetic field and put sensors on your spacecraft to tell how it's oriented, to some extent where it is in the orbit, and actually use magnets on board your spacecraft to orient it by aligning it and not aligning it with the magnetic field. In deep space, you don't have any of that. So with the 2 Marco satellites, and I'll talk about their technologies in particular, so these are the first 2 that have actually successfully gone into a space beyond low Earth orbit in the CubeSat form factor. So when you go beyond Earth, some of the issues you have to deal with is, A, the Earth is much farther away. So instead of being hundreds of kilometers from the surface of the Earth, you're now millions and billions of miles or kilometers away from the surface of the Earth. So your radio has to be more powerful, your antennas have to be bigger, and right now, the only way you can really communicate with spacecraft that far away is through the NASA Deep Space Network. It's an array of 12 satellites, or 12 satellite dishes around the globe, and they're spaced about 120 degrees apart, so you can get continuous coverage of anything in the solar system. And there's 34-meter size and a 70-meter size, and in order to take advantage of that, you have to have a radio that is compatible with this network. But what it gets you is communication with your satellite and a way to figure out where your satellite is and how fast it's going and where it's going, just based on the radio signals. So if you don't have GPS, you kind of need something like this. You also don't have a magnetic field to torque against and orient your satellite. So any way you want to move your satellite or change its position, you have to bring it on board. And that usually takes the form of propellant of some sort. And in interstellar space, you also have, or interplanetary space, we're not in interstellar with CubeSats yet, there's a much more extreme thermal or radiation environment. It's a harsher environment that you have to deal with. When you're closer to the sun, your satellites get a lot hotter. You have to deal with thermal issues that you don't necessarily have to deal with around low Earth orbit. Obviously, the farther away you get from the sun, the dimmer the sun is, the colder it tends to be. And not only is it colder, now because the sun is dimmer, you have to deal with less power being generated. So most CubeSat missions use solar panels and batteries very effectively. Missions like Cassini and Voyager had radioisotope thermal generators on board to generate power when they're too far away for solar panels to be effective. Those have not flown on CubeSats and SmallSats, so you have to get creative that way too. So Marco, as was mentioned several times, the Mars Cube 1 mission, these were 2 satellites that were launched with the InSight lander. So NASA launched a mission called InSight to Mars in 2018. It landed on the surface of Mars in November, the Monday after Thanksgiving. And the orbit of the orbiters that are around Mars weren't quite in the right position to get the data back real time. There was an orbiter that flew over while InSight was going through its entry, descent, and landing to pick up the data, but it wasn't going to it wasn't going to get the data back to Earth until several hours after the lander had actually landed on the surface of Mars. So very shortly before InSight launched, at least very shortly before it was supposed to launch the first time, they came up with this idea of, well, could we fly CubeSats along with it to be in the right position to relay that data back? So the two Marco spacecraft actually launched on the same vehicle that InSight did, and it was kind of in what we consider steerage class almost. The dispensers were put right next to the engine bell of the upper stage. InSight was inside the fairing, all nice and protected. But the two Marco satellites had to be in the correct place at the correct time to relay that data back from InSight. So that was one of the primary things that Marco flew for. And it was to demonstrate this architecture of these small satellites providing a critical mission support for a primary mission like InSight. But in order to do that, both satellites had to survive 6 months in this brand new environment with technology that had never flown before. So some of the key technologies that were developed for the Marco mission are radio and antennas. They have to be compatible with the Deep Space Network. They have to be big enough in order to get enough gain to send all that data back to Earth. So this pattern might look familiar to you. It's a reflector antenna. It's essentially what IceRA flew, just modified for a different wavelength. So a lot of the technology that's developed for low Earth orbit, like Travis mentioned, is then flown in deep space because it gives you a lot of the same advantages. Same thing with the deployable solar arrays. So again, Marco went by Mars. It's about half the power that you're getting from solar panels at Earth. And so we had to have these deployable solar arrays to get all the power we needed to perform the mission. And then we also demonstrated a propulsion system. So there was a cold gas thruster system. The volume of the propellant itself was about half of this 6U volume. And there were tiny little thrusters. You can't even see them in this picture, but there are 8 of them on this face of the satellite. And the propellant on board was fire extinguisher fluid. It was this cold gas, and you heated it up and spouted it out in little spurts. And that was enough to change and adjust the trajectory of each Marco spacecraft so that we flew by InSight during its entry, descent, and landing. There we go.
Marco A and Marco B have telemetry.
Ground stations are observing signals consistent with parachute deploy.
Marco Alpha, Marco Bravo, maintain lock status.
Lander separation commanded. Altitude 600 meters. 200 meters. 50 meters, constant velocity. 17 meters, standing by for touchdown. Touchdown confirmed.
We not only got the data from InSight as it went through the Martian atmosphere in real time, but we saw the first photographs after we hit the ground.
It's just a great tribute to the whole Marco team. They exceeded all of our wildest expectations. They both worked perfectly. We just opened a door to a new class of planetary science, thanks to the Marcos.
This was seen all around the world.
Crowds watched live in LA, Chicago, and New York.
InSight was followed to Mars by 2 miniature NASA spacecraft called Mars Cube 1 or Marco.
Shortly after landing, the first picture relayed by 2 miniature NASA spacecraft called Marco.
But on board Marco itself, we had one more gift. This image was taken from Marco 10 to 15 minutes after EDL itself happened.
So this is the picture that Marco took right after InSight EDL. So this is I love this picture. So like IceRA and like RainCube, if you have a deployable on a CubeSat like this, you want to have a camera on there to make sure it works. So we had the equivalent of like a flip phone quality grade camera, but it's a CubeSat. But you can see the feed here from the feed going onto this reflector array, and then this is the flat high gain antenna. You can see the edge of it, and we actually compared it to pictures we took on the ground to verify that it did deploy fully. But we had this camera on board, and even though it's not a great quality camera, you get Mars, which is amazing. And so our navigation engineers overlaid where the landing locations are for a lot of other missions that have flown to Mars. So this is a very cool thing to see from something the size of a cereal box. So the applications that Marco kind of enabled to go into deep space, so a lot like low Earth orbit, these CubeSats are enabling a lot of different kinds of mission architectures. So one is, like Marco, performing functions to support a main mission like InSight. In the case of Marco, is a communications relay capability. There's a mission that the European Space Agency is flying in a few years called Hera that is visiting an asteroid called Didymos and its companion. And it will be carrying 2 spacecraft. Unlike Marco, these spacecraft will actually be carried on the mothership. And they will have science instruments on them to complement that main mission. So now we're talking about CubeSats and SmallSats with instruments on them performing science to supplement a mission already going to another body. You can also take that a step farther and go even farther out into the solar system, where these outer planets have really interesting moons and really interesting behaviors that we don't really understand. So you can have almost disposable or single-use probes. They won't necessarily be in a CubeSat form factor. Like I mentioned, if you go beyond low Earth orbit, you have all these challenges in terms of power generation and data volume and thermal and everything that you have to deal with. So it might not look like a cube, but a lot of the technology being developed is directly applicable to missions like this. And then they can also do their own science with a whole flock, to use the planet term, of these small sats. So you can apply the same principle of using a constellation or formation flying in low Earth orbit and apply it to either observing locations beyond the solar system or even going to locations beyond the solar system and making these observations. So the next upcoming event in small satellite deep space applications is EM1. So this EM1 stands for Exploration Mission 1. It's the first launch of the Space Launch System. And the Space Launch System, or SLS, is a heavy lift launch vehicle in development by NASA. And so the first launch of this is going to carry the Orion spacecraft nominally to the moon. But the first demonstration launch will actually have 13 of these 6U CubeSats on a ring that sits underneath the Orion payload. They're called the Lucky 13 CubeSats. And they do a variety of science and engineering demonstrations. So of these 13 missions, 4 of them I think come from NASA, and then the other ones come from universities even, and organizations around the world. So it is a very global effort to put these satellites into interplanetary space. And they're all going to different locations. So a lot of them are going around the moon, and they're demonstrating these new propulsion capabilities in order to get these small satellites into a lunar orbit. They're also demonstrating new communications capabilities and new science instruments and ways of generating power and actually staying alive in interplanetary space. But they're also capitalizing on a lot of the technology that was developed and flown on the Marco mission. 6 of these CubeSats are using the same radio, or the next generation version of the radio that flew successfully on Marco. So just highlighting a couple of them that JPL is involved with. So NearEarth Asteroid Scout that I'm working on, it's a collaboration between Marshall Space Flight Center and JPL. So Marshall Space Flight Center is a NASA center in Alabama. They're managing the mission. And this mission is actually using a solar sail as its primary method of propulsion to get these spacecraft to a near-Earth asteroid. And there's a camera on board to image and characterize and get more information about small near-Earth asteroids that are difficult to characterize from the surface of the Earth. Another one that JPL is involved with is called Lunar Flashlight. JPL is managing this mission. The flashlight is a laser on board that will illuminate permanently shadowed craters on the moon. We know there is water ice in these shadowed craters. So Lunar Flashlight will fly in an orbit, a very highly elliptical orbit around the moon. It only gets about 15 kilometers from the surface of the moon when it's at the South Pole. And it will illuminate these craters, and then there's a reflectometer instrument on board that's tuned to water wavelengths that will detect water ice and try to map where that ice is in these craters. And it's also demonstrating a new propulsion capability. It's using this green monopropellant fluid, which is, it's more energetic than a cold gas like a fire extinguisher. It's less energetic than something like hydrazine, but it's also not as toxic, so good. Another thing that JPL is involved with, this is Sunrise. It's another fleet of 6U CubeSats. This is currently in a study phase right now, and it's been proposed to NASA's Small Explorer Call. And I do want to point out here that NASA has regular calls that go out for missions to do science for Earth science, astrophysics, heliophysics, planetary science. And more of these calls are being expanded to include CubeSats and small satellites, because in the last few years alone, the number of missions who have been able to demonstrate really good science, like Travis talked about with RainCube and Tempest D, has really shown the community that these are viable science platforms now. So the proposal calls have started to reflect that. And so this is flying a constellation of 6U CubeSats in a geostationary orbit. So it's still around Earth, but I'm considering it kind of interplanetary because it's far enough away that you have to do a lot of, you still have to take into account a lot of considerations that are more like interplanetary space than like low Earth orbit. And the purpose of Sunrise is to observe the sun, and essentially it's acting as a 10-kilometer radio telescope. You can never launch a 10-kilometer telescope, so they're using these 6 CubeSats to synthesize that aperture by flying them in a loose formation. And this I stuck in there. You'll notice it's not a CubeSat, but there's definitely a cube element to it. So this is the Mars helicopter. It is flying with Mars 2020. It's supposed to launch next year. And the helicopter is kind of a companion to the rover. Its mission is to fly around and be able to take pictures and then relay the pictures of the terrain and things back to the rover. With helicopter and similar missions like that, you don't launch it in a dispenser. It's not what someone might consider a real CubeSat. But a lot of the technology advancements that came with the CubeSat and SmallSat paradigm involves shrinking all of these technologies that would normally fit in a satellite the size of a bus, like Cassini or Voyager for the people in this room, and really making very capable satellites and payloads that are very small. And so there's no reason why you can't use these small, new technologies in bigger missions or new missions that aren't the shape of a cube. So the next couple charts are sketches, like literal sketches. The graphic designer who did these, her name is Kat Park. She works here at JPL in a studio. And the idea is, none of these are all mission concepts, but it's kind of an idea of what kind of missions you could see in the not so distant future with these small sats and CubeSats. So one is very similar to Marco, flying small sats to Mars. These would probably be a little bit bigger than a lot of the 6Us that we've been presenting, but they would have their own propulsion, they would have these big solar panels, and they could go to destinations like Phobos and Deimos, and they could use novel propulsion capabilities like solar electric propulsion, or even ones that we've never thought of to do cool science without a primary mission to go along with. There's also this idea that you could go to an asteroid and fly a small sat or some probe through plumes to get kind of in situ measurements of what might be there. You would never want to fly a big, expensive spacecraft because it's a little bit risky with particles flying at your satellite. But it could and it could either communicate directly to Earth, or you could have an architecture where there's a mothership sending that information back to Earth and making its own measurements potentially. Or you could send them to a comet, and in this case, the comet's it's spewing a lot more particles out there as the tail forms, and so you could fly a whole fleet of them and maybe even have them start talking to each other to coordinate better measurements. And again, you could have them talk back to a mothership, you could have them talk back to kind of a leader spacecraft back to Earth. And so a lot of these concepts is not just physical. You don't have just physical limitations in terms of getting bigger antennas and bigger solar panels and bigger propulsion systems. You also have to make the satellites smarter. So a lot of autonomy and advances in computing capabilities would really enable missions like this, so the satellites can kind of think for themselves and decide which observations are the most interesting, or figure out if they lose a satellite, that's fine, we can reconfigure to still get the measurement we want. And thinking even farther out there, so if you're going to an outer planet, could you bring a bunch of really small sensors, and instead of getting, again, like a lot of low Earth orbit applications, instead of sending one spacecraft to get a bunch of measurements over a certain period of time, if you send a whole flock of spacecraft, a fleet of really tiny sensors, to get a whole distributed spatial set of measurements at a specific point in time. It's a different kind of measurement technique than has historically been done, and it's very exciting, especially if you're kind of on a flyby trajectory and you only get one shot. Similar thing if you want to go into orbit, or a slower flyby, or something like Clipper, where it kind of goes, Europa Clipper is a mission that JPL is working on to go to Europa, a moon of Jupiter, and it kind of, it's not quite a flyby, but it doesn't go entirely into orbit. It gets a bunch of orbits around Europa and then leaves. But if you brought a whole swarm of CubeSats or SmallSats, these would probably be bigger. They could, again, do that kind of formation flying and coordinated architecture of measurements and science that you can't do with just one spacecraft. Or you could send a whole fleet of them, a lot like Asteria, and look more into interstellar space, and a whole fleet of them to look at, of little imagers to look at one star instead of one telescope looking at multiple stars. Or even, what would it look like if you tried to send one of these interstellar? So and this is actually a CubeSat. So going into interstellar space, you have to go really far, you have to go really fast. It's a lot easier to do that if it's really small. So with these new advances in miniaturizing technologies, could you potentially envision something that's the size of a postage stamp that actually has all of the capability it needs to go beyond the solar system? I don't know, it's conjecture. So yeah, so interplanetary travel with CubeSats has really only been around for the last 5 years. As I mentioned, of the 1,000 CubeSats that have launched, 2 of them have gone below low Earth orbit. So it's still a very new field, but it's a really exciting field, especially because a lot of these technologies that have been developed for low Earth orbit are directly applicable, in many cases, to flying beyond low Earth orbit. And it'd be really interesting to see how many of these bodies you could actually have small satellites on in the next 10 years or so. So that is the end of my talk. Thank you very much for listening, and I believe we have questions now.
All right. Well, thanks, Annie. Well, this is the part of the show where we transition to your questions. So if you have a question here in the audience, we'll have a microphone in the center, and you can step right up there to the middle aisle and prepare your question. And if you submitted a question online on the YouTube chat, we'll get to a couple of those as well. So do we have any questions here? Here comes John with the microphone. Well, I'll get started because I have all kinds of questions. Just since you both talked a lot about how you started your careers working on CubeSats, how has this topic specifically shaped your careers as engineers?
Go ahead.
Okay. Well, I kind of maintain that the experience that I got in undergrad, and probably more in grad school, of actually building and flying one of these satellites, I don't think I would have gotten the position I did on the Marco team without having that experience. And so there's a lot of getting real hands-on. Space is hard no matter who's actually flying the satellite into space. So I think it's giving me a lot of hands-on experience and a much more in-depth appreciation for how difficult flying something in space is and the challenges you have to overcome and kind of experience, banging your head against the wall trying to figure out why it's not working before you even get out of school. So I think it's invaluable to have that hands-on experience.
Yeah, and something I think is unique about the CubeSat form factor is, if you remember, I showed my picture of how we tried to jam everything we could into the box. But that means that you as an engineer can actually kind of understand everything that's in that box. All the subsystems are touching, literally and electronically and everything else. But you can begin to understand how your power subsystem connects to everything else, how your radio subsystem is connected to everything else, how your payload requires the whole spacecraft to perform perfectly. And working on these payloads, when one thing goes wrong, you kind of see how it flows through the system, and when something goes right, you see how it flows throughout the system. And that's something I think is unique. When it's small, you actually have the capability as a single person to understand everything you're working on. And that was kind of a good introduction to all sorts of different disciplines of engineering and science and physics and other topics through school, and both here at JPL.
Hey, how you doing? Go ahead.
All right. Given that there are limited numbers that can be launched, even though there are 1,000 out there, I suspect there's a great desire for more by those who are making them and studying them. I'm curious about the decision-making that's involved, or the competitiveness to end up on a launch vehicle to get out there. You showed, for instance, that there would be 13 on an upcoming mission. How did you decide, or how did somebody decide?
So I won't quote the number, but there are actually many companies that we call new space companies. So new space are kind of these aerospace companies that have just come around within the past decade or so. And there's actually several companies that are competing, both through NASA funds and privately funded, to actually develop this whole kind of small fleet of rocket launchers. So much like that Electron rocket I showed from Rocket Labs, I think there's Virgin Orbit, one company, Vector, Firefly, are all companies that are actually being designed for kind of this 100-kilogram class payload. And whether that 100 kilogram is one spacecraft or a company that wants to launch 33-kilogram spacecraft, they can do it. So there's actually a huge investment from the launch services side to actually meet the commercial demand from these SmallSat, or especially constellation companies.
And to your question on the EM1 payloads, so some of them, like the ones that were proposed, they're funded by NASA, is the proposal process a lot like you'd have a Discovery or New Frontiers kind of mission. There are actually 3 CubeSats on there that are part of a thing called a CubeQuest competition. And it was mostly universities, but some hobbyists actually in there that had to go through a series of, I forget what they called them, but essentially
like
stages.
Grand challenges?
Yeah, grand challenges to kind of milestones, and they were whittled down from, I forget how many initially proposed, but then they've filled 3 slots of those 13. So it is also partially competitive.
Hey there. You got a question?
Oh, yeah. Thanks for the great talk. Question on Europa and Enceladus and CubeSats in that domain. How much easier or more complicated are planetary protection needs in the case of building something like SIL for smaller craft that are going to travel into those environments?
It's a really good question. So you still have to meet the planetary protection requirements, kind of no matter how big you are. With the Marco spacecraft, we also had planetary protection requirements we had to meet. And there are a couple ways to do that. One is to show that your trajectory, if you're completely off and kind of a brick, and that's how you essentially, to be safe, that's kind of what you assume that the CubeSats are, or a secondary payload is. One way is to show that your trajectory will never impact something that is protected in this planetary protection environment. The other way is to do a lot of simulations and put what's called a bioburden on the satellite. And so you basically give a metric for how clean the satellite has to be when it launches to get the probability of it bringing unwanted life with it below a certain threshold. So you have to do that same kind of analysis on a small satellite as you would with a larger satellite. With the Marco process, we were able to tailor it a little bit and kind of, through measurements, show that we were meeting requirements without having to kind of jump through a lot of hoops to do it in a more analytical kind of way.
Well, and I heard you mention SILF. So for those in the audience, SILF was a small sat concept that JPL produced, which would fly through a plume on Europa. I mean, it was a trash can-sized satellite, so maybe like a propane tank is about 80 kilograms. And from planetary protection in that case, we actually leveraged some of the CubeSat concepts. So by going from a square form factor to this round form factor, we actually designed it to basically meet the planetary protection requirements of Europa. And because it was small, we took the approach of saying, what if it does impact, and designed it to be that, designed it to basically meet those requirements. The thing that made it kind of CubeSat-like, even though it was cylinder-shaped in that Jupiter's environment, was that it was actually in a dispenser of its own that actually acted as the biobarrier to keep outside contamination from getting on that probe itself. So that's kind of a leveraging of those technologies, which actually was really interesting.
Thank you.
Cool. So I've got a twofer for you from YouTube, from our viewers on YouTube, because I think they're connected. So the first question comes from Yan, who asks, is the probability of a CubeSat collision with space debris so small that it's not a concern? But Sumiyajit asks, what is the lifetime of a CubeSat? And am I right that those are connected?
They are connected. So in the case of RainCube, we had our deployables. And there's actually, although there's very little atmosphere in our altitude, we're up at about 400 kilometers, which is similar to the space station. Depending on if we're flying with our solar panels like right in I would call it the wind, but depending on how much drag you have to fix your life. So we designed RainCube for a 3-month mission, thinking it might come down as quickly as 6 months, but it looks like it's going to actually stay up for a few years. As you get a little bit higher in the few hundred kilometer category, it might take more years. But generally, there is a requirement that you have to show that your spacecraft will deorbit within 25 years. So you can do that through either analysis saying that the atmospheric drag models say you will, or perhaps you put on a propulsion system to push you down. There's also concepts that have these giant inflatable airbags, basically to increase their drag to actually pull them down faster. I don't know if there's been a collision.
I don't know of one with a CubeSat.
So, not yet.
Okay. Fingers crossed.
Never.
So, hi, got a question there?
Yeah, I'm so sorry, I'm new to the CubeSat technology, so sorry if I misinterpret the acronyms. But my question was, how long is the CubeSats that are out there? What's the longest that they've been out there, the thousands or so that you had mentioned that are up in space? What's the longest time that they've been out in orbit?
So one of the first ones that has flown is actually still working. It was, yeah.
What was it?
I don't know the name, but I believe it's a Japanese one, and I'm going to have to look up the name now. But yeah, it's still operating. It's at a slightly higher orbit, so I think that one in particular might stay up there for a little longer than 25 years. But yeah, that's the longest running one that I know of. A lot of the more recent ones are flown to an International Space Station orbit, and those are low enough that they kind of come down within a few years, give or take. And for those, I think most of those have actually been limited by the lifetime. They've still been working. If there's kind of within the first day or like early part of the mission, if there's kind of a bimodal failure. So there's some that die very quickly, but if you kind of get past that initial hump, they actually tend to last a pretty long time.
And I'm trying to get my brain wrapped around what keeps them staying up that long. Like, what's the energy that they use?
Oh, they're in orbit. So just like the International Space Station and other big satellites out there, they're designed and high enough and going fast enough that they're essentially continuously falling, but they're falling at a speed high enough and an altitude high enough that they will never hit the surface of the Earth.
So they keep sustaining that. Okay, thank you so much.
But you could put a propulsion, like some missions, like Marco, which have a propulsion system, you can actually use that to actually keep yourself up. So in the case of RainCube, if we had a future mission that we wanted to last for many years, a future concept could have a propulsion system that would actually keep us at the specific altitude we needed for science.
So I heard you mentioning that the CubeSats are starting to even be used in high schools and middle schools. Are these seen in like the future more as like an educational tool or like, introduction into like, aerospace engineering class type of thing?
Oh, well, I guess, yeah, so I know that some of the schools that have been featured, like the high schools and middle schools, have actually been partnerships with NASA centers. So similar to, I think, you might see like some robotics programs that have partnerships, but they are traditionally used as kind of an educational platform. With the proliferation of the standard, you've actually seen companies that are basically developing kits that you can buy and you can take to your school and you can learn kind of the first principles of engineering. But then it kind of has this open, perhaps has an open interface for where you could plug in your own camera or plug in a different payload. So they've done a lot of the engineering to kind of make something that will get up there and power on and communicate back to you, and then you can kind of grow from there. I'm not too familiar with some of these packages, but I'm sure it'd be easy to find, and it'd be a great opportunity for young people. I wish I had been able to work on CubeSats when I was in elementary school, but I was just, I don't know, eating Play-Doh or something.
Yeah, so NASA Ames is actually running a program called TechEdSat, and so they fly a lot of, essentially they fly the main spacecraft, and then you can kind of buy a slice or design a slice to go in that CubeSat and kind of fly your own payload along with it. So that's another way that it, from kind of a more educational perspective and a little bit of a smaller bite to chew on.
Good luck.
Hi, my name is Usang Park from South Korea today, and I prepared some questions about, in addition to her question, do you think it is possible for individuals to explore and use space by CubeSats in the future?
Can you repeat the question again? Sorry.
Do you think it is possible to utilize the space and explore the space by using CubeSats?
So I think are you asking if an individual person might be able to make their own CubeSat?
Yeah.
If you have the right skill set, yes. It's almost like building a computer, but the computer has to work a lot farther away from you, and you have to be able to talk to it, and you can't touch it if something breaks. So it's a lot more complicated than you might initially think.
But to add on to that, I think with the proliferation of these small sat companies, you now have companies that are dedicated to providing ground stations. So they're building the antennas, and they build a beautiful web interface for you to just log in, and you can point the antenna at your CubeSat. So there's been a huge push as all these other companies have grown for, I think, a great opportunity for individuals to start getting their own access into space.
And thank you. And I have read the fact sheet about Marco. And do you have any special reason to use identical two CubeSats?
Mostly because when you build two of the same thing, you know how to do it. So if you build one, you know exactly how to build the second one. You don't have to change anything.
There's also redundancy. So I actually worked on the other side. I was actually working on Insight during the EDL day. And when both Marcos were actually collecting the data, but that way, in case there was a hiccup with one, if the other one was still there, we'd still be able to get it back, although they both worked perfectly. So
when they had to.
And one more. And during the way to Mars for the two CubeSats, and it will be exposed to very high particles and radiations. How can we simulate the situation in Earth?
There are actually test facilities, a few of them throughout the world, that do radiation testing. So it's a very controlled test, but you essentially you can send an ion beam to simulate like high energy particles. You can also have it just sitting next to a source of radiation and kind of getting a total dose accumulating on it, and you essentially put test boards in there and just see when they fail.
All right, thanks a lot. We're going to take another question here from YouTube. We have SSArt98 who's asking, what are the most used or preferred materials for building CubeSats? You talked about tape measures from the hardware store. What else do you use to make these things?
A lot of aluminum. And I remember once when I was in the university, we actually bought like 5 feet of an aluminum block. It was 5 feet and it was 5 inches on each side. And we actually ended up slicing that up. And then we milled out the insides and the outsides to actually make the walls of our CubeSat. And I remember thinking like, oh, we got like, 300 pounds of aluminum, and it was only like $200, for all of that. So a lot of aluminum, a lot of circuit boards, a lot of wiring. Wiring takes up a lot of the volume, especially when you realize that wires have to bend around each other. So that was one of the challenges. In school, one of our preferred tools for assembly was actually using dental tools. So we would actually like stick, when they used to scrape your teeth, we'd actually like stick that inside the CubeSat and use that to pull the wires through our little nooks and crannies.
Hey.
Yeah. Hey, so that gentleman's question about individuals using or building and using CubeSats to do their own sort of private exploration of space got me wondering, what are the legal regimes that govern the launch of these crafts? Is the same as just launching larger satellites? In other words, how do you get that clearance? Who gives the clearance, et cetera?
Yeah, so a lot of it is the FCC, which is, I don't know, like Federal Communications Commission? Yeah. So Spectrum, and one of the big things you really need to get approved regulation-wise is the communication spectrum you're using, the band you're using. There's, in the frequencies that are typically used by CubeSats in like the UHF regime specifically, there are a lot of assets using that band, so it can get very noisy. And so there are restrictions on what kind of bandwidth you can use, what kind of power levels you can have, when you can transmit them. So that's one of the big ones in terms of regulations for flying these.
All right, well, there's a question from YouTube from Ultimate, who wants to know, how are you planning to improve these satellites? How are you, you talked about some of the places you want to send them and some of the things they could do, but what would you like them to do better? Do they need to be smaller?
Ooh. I think we're doing a great job right now. Well, so Anne mentioned a lot of the grand challenges that I think CubeSats have. Earth is really nice because it's, you have sunshine, but you have eclipse, you got the magnetic field. Designing everything, I think, in my opinion, ultimately boils down to power. So you need power to communicate back to Earth at these incredible distances. And you need power to keep yourself warm at these incredible distances. And one of the grand challenges is, once you start going out farther in the solar system, how do you generate enough electricity? So, we have Voyager sitting over here, which used, the radioisotope power sources. We have Europa Clipper, which is using solar panels out at Jupiter's distances, but those solar panels are so huge compared to the size of the actual spacecraft itself. And on the small form factor, it can be very difficult to fit these very giant arrays onto such kind of a small box. It doesn't really quite scale as nicely. So I think a grand challenge is, how do we get enough power when we're far away? I think we know how to communicate and keep ourselves warm when we're there, but.
I would personally like to see them get a little bit bigger.
Everyone says that. Everyone says, oh, the 3U is the perfect size, and the next, you saw all of ours were 6Us, and it was like, but 12Us, those are the future now, so.
Cool. Hi there.
I'm interested in the dream of the future, and that's interstellar and going to some other planet or star and bringing back images. Do we have electronics that are capable of handling that sort of hard life, or hard radiation? Because you're going to have to do a nav system, and you can't communicate at light year distances. How are we getting in there?
So to my knowledge, we don't have any technology right now, but I know a lot of people are interested in doing that, and so I'm sure we'll see it at some point.
Comes back to power.
Yeah.
Need
power.
Power to transmit.
Propulsion.
Had a communications question. Given the subarcsecond pointing accuracy of Asteria, what are your thoughts on optical communications, Opal style, from CubeSats within cislunar space to Earth?
So optical communications is an active area of research, and there have been a couple of payloads that have flown and demonstrated the capability to do optical communications from a CubeSat platform. From distances beyond low Earth orbit, it becomes more challenging for any kind of spacecraft because the pointing does have to be better. I think there's at least one of the EM1 payloads that might be demonstrating that, but I might be thinking of a different one.
Yeah, and there have been universities and other institutions that have worked on optical communication demonstration technologies.
Thanks.
All right, last question. The honor goes to you, sir.
Sorry. So regarding CubeSats, you know how in space we have larger satellites communicating with Earth, right? I'm wondering if we could have CubeSats to be the new future of technology to communicate with the rest of Earth. If so, how?
Yeah, so there are companies there's a company called OneWeb, and I believe SpaceX is looking into this too, of sending constellations of small sats, not necessarily CubeSats, but definitely small sats, to do just that, to kind of provide this global internet or global communications capability. So it's, especially with with advances in shrinking this technology to fit on a smaller platform, obviously the smaller it is, the easier it is to launch, the easier it is to launch a lot of them, so that is a very, very attractive thing to want to do.
Thank you very much.
Well, folks, that's all the time we have for today. Thanks to everyone for joining us here and online, and of course, thanks to our speakers. Join us again next month for a look at how we develop new space missions from concept to the launch pad. So we'll see you then. Thank you so much for joining us.